Audio Jungle. Audio Jungle.
Like this is the second lecture of rocket propulsion, and in previous class we had seen that equation of thrust for the rocket and condition for the maximum thrust for the rocket. Okay, now we'll see the effective exhaust velocity. Okay, it's a effective exhaust velocity. So as the word only you can understand, the effective exhaust velocity is often used to compare the effectiveness of different propellant in producing thrust in rocket engine, right? Means you have a different type of rocket engine like solid, liquid, hybrid, or solar, nuclear. Okay, so these type of the engine we have, but propellant based engine we have a three, like solid, liquid, and hybrid. So if you want to compare the different propellant producing thrust rocket engine, so one parameter you have to use, and that is called effective exhaust velocity. Okay, as you know the word thrust vectoring, so actually the velocity profile at the exit of nozzle need not be one dimensional in nature in practical situation. Okay, so we have to check that nozzle directly whatever the velocity exit flow we are getting at the nozzle, it is not in one dimensional, it is in different direction. In the sense it is like, I will draw the diagrams, it will be clear. Suppose this is the exit of the nozzle. Okay, suppose this is the nozzle we have here. Okay, so in this case whatever the flow is coming, it is in this way. Check, this is the exit from the nozzle. Okay, this is the flow velocity here, similarly here also, and in between it is like this. So think, so what we are having here, that flow is what coming like this, and it is very practical thing. Okay, why this direction, that flow is what following, it's not a very challenging thing to understand, it's very practical because the flow will follow the path. Okay, that ducting path, and duct is what like this, so obviously flow will come like this, and in between that flow will follow this path. Okay, now so this is now the velocity. Okay, that exit, at exit this is the direction of the flow, you can understand in this way. This is the exit of nozzle, and obviously now what you are going to do, you are going to write effective exhaust velocity or equivalent velocity. That word also you can use, effective or equivalent. Okay, why we are interested to calculate equivalent? Because see, here the flow is what going in this direction, this particle, you can say here the flow is what in this direction, here the flow is what in this direction. So what we are going to do, we are going to vectorically we are going to find the resultant of all the direction of the flow. Here see the multiple direction we have. This is follow in this direction, this one is follow in this direction, and similarly here it is following in this direction like this, and this is following in this direction. So in this way, whatever the calculation of thrust you are getting, it is difficult to find the resultant force, because thrust is what resultant force, and equal action and reaction. So whatever the propelling force you are getting, it is exactly just opposite to the this thrust. Yes or no? Opposite to the whatever the exit velocity, and because of exit velocity into flow rate will give the momentum, and change of momentum will give the force. So whatever the force at the exit, just opposite of it will get the propelling force, and because of that propelling force, that system will move in forward direction. That is very common thing. So if you check, these are the different direction here. See, this is the different direction. Okay, this is what different direction you can say, and here this is different direction. Okay, actually you are interested to get the all whatever the exit flow we are getting here, all we are interested to get in same direction, in this direction. Then only you will get the force, resultant force, and that resultant force will try to propel this body in forward direction, and this will be the thrust. Yes or no? So the thrust vectoring in the sense what? That resultant vector sum you want for all the velocity, because velocity is what? Vector component, actually vector quantity. So vectorically you can find the resultant velocity. Okay, in such a way you can get maximum thrust and maximum utilization of the exhaust velocity. So the whole you will convert in one single parameter. Okay, the whole thing here, this is the check velocity in different direction. The whole you want to convert in one direction, and that direction will be exit velocity. This is the now exit velocity. So that is nothing but vectorical sum, okay, for the velocity component. Now this is nothing but V equivalent or effective exhaust velocity. Hope you understood this. So that's the reason very common word we are using for the rocket engine, that is thrust vectoring. So hope you all understood why resultant velocity we required. Okay, to get maximum utilization of the exhaust velocity, to get maximum thrust, you can say, to get optimum thrust, we have to find the effective exhaust velocity. And this is the one by the diagram I have explained here. Now mathematically, what is the model for the equivalent or exhaust velocity? Okay, so you have seen that maximum thrust, what you had seen, I think it was T, denoted by T. No? Sorry, just sorry. Okay, so you know that maximum thrust obtained from the nozzle, we had seen in last class, it was m dot p into v. Okay, and this is what v equivalent now. This is now v equivalent. Okay, I told you effective exhaust velocity or equivalent exhaust velocity is often used to compare the effectiveness of different propellant in producing thrust in rocket engine. Okay, now if you check what is the velocity here, v equivalent, so this v equivalent is nothing but T divided by m dot P. What is T? T is nothing but thrust. T is nothing but thrust divided by mass flow rate of the propellant. Okay, now in very common, you know that thrust, if you write the thrust equation, yesterday I had derived in my last lecture, m dot P VE, okay, plus PE minus PE minus PA atmospheric pressure into exit velocity. So what is the V effective or equivalent? It is nothing but T divided by m dot P. Okay, and here if you write m dot P into V effective plus PE minus PA into AE divided by m dot. So this is nothing but plus PE minus PA, okay, into this is what exit area AE m dot P. Okay, so now where V equivalent is the effective exhaust velocity that would be produced equivalent thrust which could have produced due to the both momentum and pressure components. So this is what this, if you go for the calculation of the that thrust, so thrust will be what, two type of thrust I had explained, momentum and pressure. Okay, so the equivalent or effective exhaust velocity that would be produced equivalent thrust which could have produced due to both momentum and pressure component of thrust. Okay, so this is what the effective exhaust velocity. If it is asked, you need to answer it. All right, now see the equation. If PE is equal to PA, what is the mean of it? The exit pressure is same as the ambient pressure, then the effective exhaust velocity V equivalent becomes equal to nozzle exit velocity. Okay, so at that time this effective exhaust velocity will be equal to exit velocity when PE is equal to PA. But two case I will write. Point one, if we have PE is equal to PA, which is the optimum expansion, then that effective exhaust velocity will be V exit. Check this. Yeah? Point one. But in general, if PE is greater than PA, or you can say PE by PA less than 1, then check, then this bracket PE minus PA will have a positive value. So V equivalent is equal to VE plus some constant. What is the mean of it? Its meaning is, if you calculate that effective exhaust velocity, it will be less than exit velocity. It will be less than exit velocity. Okay. Then you can say V equivalent is less than VE. Okay, less than nozzle exit velocity. Check it. No? All right. Okay, correct this. Fine. Now this is the one thing. Now very important, effective exhaust velocity. Effective exhaust velocity. This is they are asking in exam. Okay, so please listen carefully. Effective exhaust velocity. Effective exhaust velocity in terms of exit Mach number. Okay, in terms of exit Mach number. So the simple one only. This is the nozzle. Okay. Now if you check here, this area is nothing but exit area. So pressure will be PE. Okay. And we have a flow like this. Okay. We exit, and this is the effective exhaust velocity resultant. So what is the mass flow rate? Mass flow rate. It is m dot p. It is nothing but rho e, AE, and VE. Basic formula, right? Now you have seen that formula, which is check this one. This is what V equivalent is equal to VE plus PE minus PA divided by m dot P into AE. Okay, you can write this effective exhaust velocity. So we can have effective exhaust velocity now, which is nothing but VE plus PE minus PA into AE divided by m dot P. Okay. Now instead of m dot P, we can write that value. So what is the V effective? VE plus PE minus PA divided by m dot P. You can write rho AE into VE. Area is AE. You can cancel this. So if you take VE common, 1 plus PE minus PA, AE cancel out. Here you will have rho E into VE square. AE cancel out. Okay. Or you can write VE in bracket 1 plus. We can take common PE, so it will be PE divided by rho E into VE square. It is 1 minus PA by PE. Simple mathematics only. Now, so V effective is equal to, and this is necessary part. Okay, so PE is nothing but rho RT. So rho E R into TE divided by rho E into VE square 1 minus PA divided by PE. If you solve this, what you will get? we cancel out, it is nothing but VE 1 plus we have R into TE, okay, divided by, we can do one thing, what is ME? ME is nothing but VE divided by root of gamma R TE. So rho is cancel out. What is VE square? VE square is nothing but ME square R TE in bracket 1 minus PA by PE, right? Now TE cancel out, R cancel out, what you will get? Gamma, I think it will be there, na? Gamma RT. So here we can write gamma. Now fine. So V effective exhaust velocity is nothing but VE in bracket 1 plus 1 upon gamma ME square. See, this all value RT will cancel out. You will have 1 minus PA by PE. This is the value. Okay. And this is very useful formula. Okay. Need to remember. Again, this formula is what in terms of Mach number, exit Mach number. See, if exit Mach number they have given and they are saying calculate effective exhaust velocity, so you can do that. One more thing, if PE is equal to PA, which is optimum expansion, then effective exhaust velocity is nothing but V. Check it. These formulas need to remember, need to practice at least one time because questions they are asking based on it. Hope you understood. Now, this is very important, okay? So, if you say that exhaust velocity, what is the dependency of the exhaust velocity? So, it is totally depending on the propellant properties, thermodynamic properties, okay? What is the density of the propellant when it is burning in combustion chamber, then what is the maximum temperature it can produce, what is the maximum pressure it can produce in combustion chamber. Okay, so the propellant enter the combustion chamber, mix and are ignited. The gas produced is heated by chemical energy, released during combustion and expands through nozzle. Okay, so the temperature of gases in combustion chamber now you will denote by Tc, and because there is no flow intake, so whatever the in combustion chamber, that velocity will be negligible. Hence, whatever the static temperature you are going to consider in combustion chamber, it will be total temperature. Similarly, pressure also you can say. So now, if you go for this exhaust velocity in detail, exhaust velocity. So what you will do, you have see only combustion chamber part I am just going to draw. Okay. Here, huh? So you say whatever the propellants we have here, if I say solid propellant, Okay, once here we have igniter, once it is ignited, so definitely it will start burning. Once it is start burning, so it will apply pressure for the surface of the nozzle, very high pressure, and definitely the combustion is what is started here. Okay, very high pressure and temperature. So we just say this is what the throat of nozzle, this is AT, throat of nozzle, this is what exit. So I can say up to here, this point to this point, this is what nozzle. There should be clear about nozzle and combustion chamber, and this is what combustion chamber. Okay, combustion chamber. All right, now it is the throat area of the nozzle. So whatever the pressure developed here, it will be TC. Whatever the temperature developed here, it is TC. So now for the nozzle, so here in this part, whatever the pressure, it will be PC, and what is the temperature, it is TC. Okay, and this is the minimum area of the nozzle, which is called throat, and 80 is the throat area, and this is the exit. Okay, exit. Pressure is nothing but PE, velocity is nothing but VE, exhaust velocity, and obviously surrounding will have a atmospheric pressure, no doubt, because surrounding pressure will be acting over the surface of the nozzle EA, and here we have a exit pressure PE. So my point is this PC and TC will be total pressure and total temperature. There should not be any confusion. So what is the PC? Total pressure in combustion chamber. What is TC? Total temperature in combustion chamber. Okay, it's not static, it's a total. Why? Because velocity is what negligible. That velocity is what negligible in combustion chamber, because we do not have any intake, right? It is burning, and fluid is what combustion products is what coming outside because of very high pressure and high temperature. So once it start burning, so very high temperature will be there, and because of high temperature, high pressure. So that high pressure uh, flow will try to expand, and it will expand in nozzle with very high velocity. Okay. All right. Now, so how to relate this? So very basic thermodynamics relation I'm just going to use, and what it is nothing but whatever the total temperature, this total temperature will have a change in specific enthalpy. So I will write gain in kinetic energy of exhaust gases per unit mass is equal to change in specific enthalpy. Okay, obviously whatever the kinetic energy you are getting at the exit of nozzle, it is because of the enthalpy rise in combustion chamber, because in combustion chamber propellant is what burning, so definitely enthalpy will rise, and whatever the enthalpy rise we have, it will convert into kinetic energy. So whatever the gain in kinetic energy, it is because of the change in specific enthalpy. How to get that? What is the change in specific enthalpy? See, we have total temperature Tc, okay, and this is the exit, and obviously here exit will have a static temperature. So this Tc will be total temperature. I told you total temperature you can write T naught, and this total temperature will be constant throughout the nozzle, because it is very basic principle. I have repeated many times, and now also I am going to repeat. In nozzle and diffuser, total temperature must be constant. It is not going to change. Why? Because we are not adding any heat. If you check heat, we are adding in combustion chamber, not in nozzle. So in nozzle, total temperature must be constant. So this T naught will be same everywhere, T naught. No? So this T naught, you can say for the exit of the nozzle, it will be T naught E. So TE will, whatever the T naught E we have here, that is the total temperature at the exit. This is the exit, okay? This is the exit value, static, and this is what total. So this change in enthalpy will be, now we can write change in enthalpy, and it is specific. So mass flow rate of the propellant not already you have uh, taken in denominator, because per unit mass you have written both sides. Specific means per unit mass, and here it is already mentioned per unit mass. So what is the specific enthalpy then? It is Cp into delta T, and what is the specific kinetic energy? It is 1 by 2. It should be mass flow rate into velocity square, but mass flow rate we have taken unit mass, so mass is what not considered here. It is in denominator, no? And it is cancel out, you can say, both side. So this is half VE square is equal to Cp delta T, and this Cp into delta T. What is delta T? Total temperature in combustion chamber T naught E minus static temperature at the exit. This one. Okay. Now what is VE? VE is nothing but, this is also very important because gate question they had asked based on it. So please listen carefully. No? So this is the exhaust velocity in combustion chamber. This is the one formula. Okay. Number one. Number two, this also you can write in terms of pressure, because they will give the exit pressure values. Okay. So what to do in this case? So this is the exit velocity for the nozzle. You need to remember this formula. It's very special, and you have used many times this for the nozzle calculation, but I will tell you something special, like how to relate with the pressure. Okay, so this is the one formula for the exhaust velocity in terms of temperature. Now how to relate this in terms of pressure? So you know very well that Cp formula is what? Cp is nothing but also, this is basic formula, gamma r upon gamma minus 1, and isentropic relation, you know, if I take T naught E common, so it will be Te by T naught. So Te by T naught you can write, Te by T naught E you can write in terms of pressure, it is Pe by T naught E to whole power gamma minus 1 by gamma. Okay, we have to use this. So we will get, in short I am just writing 2Cp is nothing but 2 gamma power upon gamma minus 1, and T naught E I have taken common, so here it will have 1 minus Te by T naught E in root. Then what you can write, VE to gamma, okay, upon gamma minus 1. This R is characteristic gas constant. We will write universal gas constant Ru divided by molecular mass of the propellant into T naught E, which is nothing but total temperature in combustion chamber. Okay, and in root 1 minus T by T naught is nothing but P by T naught E to whole power now minus 1, and this is in root. This is the another formula. Okay, now in this formula, why I am writing this formula, there is some speciality of this formula. A speciality is what? The dependency of the exit velocity. Dependency of the exit velocity. So you can say exhaust velocity. This is the another formula. Okay, velocity depends on following parameters. Number 1, what are the parameters? M is the molecular weight. M is the molecular weight of propellant. Okay, or you can say of exhaust gases. Okay, point 2, need to remember. Okay, it's a combustion chamber pressure. Okay, P naught E is nothing but here also this is also PC. Also you can write combustion chamber pressure and combustion chamber temperature. So this PC is also you can write P naught, because that velocity is what negligible. So whatever the static value will be stagnation value. So this what you have written here, this is nothing but combustion chamber pressure, P and P naught E, which is nothing but also called PC, combustion chamber pressure. This formula indicating it is also depending on the TE, T naught E, or you can say T naught, which is nothing but combustion chamber temperature. Okay, I must say combustion chamber pressure will be P naught E or PC, not P. P is the exit pressure. Sorry, need to remove this. Now this is fine. And at the same time, we can write exit pressure of the nozzle also. Point 4 is it also depend on exit pressure of nozzle. Point 5 is specific heat ratio gamma of exhaust gases. So all 5 points you need to remember. Okay, for the exhaust velocity, these are the important points. Okay, theoretically sometimes question they are asking based on it, so please remember this. This is the dependency of the exhaust velocity of the nozzle. All right, now if you check here, in the above equation, if you check what is the equation here, see, in the above equation, this is nothing but VE. So if you check, VE is equal to 2 gamma upon gamma minus 1 RU by molecular weight, and I think in terms of temperature or what, T naught, huh? T naught, sorry, not T naught. T naught is nothing but combustion chamber temperature, total temperature. Sometimes T naught also can write TC. TC and T naught E will be same, combustion chamber temperature. But T naught E and TE will not be same. T naught E and TC you can say it is same. Okay, so T naught E in bracket 1 minus T by T naught T gamma minus 1 by gamma. This is VE, but at PE is equal to 0, VE will be VE max. Alright, so what will be the VE max value? It will be 2 gamma by gamma minus 1 RU by M into T naught T. This is equation 1 and this is equation 2. If you want to develop relation between VE max and VE, then what you will do? We will write VE max by VE. Check VE max by VE. So the first part, this side it is, you write 2 bracket. I mean root you can break it. So what you will get finally? 1 minus P by P naught, that part you will get, rest it will be cancel out, right? You can check this, VE by V max or VE max by VE, it's your choice. So you will get this VE max by VE, then you will have 1 upon root of 1 minus PE by P naught E to whole power gamma, this is the root. Okay, I need to remember this. Now we have a problem also. If you want to solve, we can solve here one problem based on the basic what I have taught. Basic we can solve one problems. Okay,